Introduction to Solid Principles. Solid principles are a set of design principles in object-oriented programming, OOP, that aim to make software designs more understandable, flexible, and maintainable. The term SOLID is an acronym that represents 5 core principles: Single Responsibility Principle, SRP, Open-Closed Principle, OCP, Liskov Substitution Principle, LSP, Interface Segregation Principle, IFP, and Dependency Inversion Principle, DET. Adhering to these principles helps developers create systems that are easier to manage, extend, and debug. Single Responsibility Principle, SRP. The Single Responsibility Principle, SRP, states that a class should have only one reason to change, meaning it should have only one responsibility or job. This principle emphasizes that each class should focus on a single task or functionality. Example: imagine a class invoice processor that handles both generating invoices and sending them via email. This violates SRP because the class has 2 responsibilities: invoice processing and email sending. To adhere to SRP, you should split these into 2 separate classes: invoice generator and email sender. This separation makes the system easier to maintain and test. If the way emails are sent changes, you only need to modify the email sender class without affecting invoice processing. Real-life use case: consider a restaurant management system. You wouldn't want a class responsible for managing orders to also handle customer feedback. Instead, separate classes should manage orders and customer feedback independently. This way, changes in how feedback is collected don't impact the order management process. Open-Closed Principle, OCP. The Open-Closed Principle, OCP, suggests that software entities like classes, modules, and functions should be open for extension but closed for modification. This means you should be able to extend the behavior of a class without altering its existing code. Example: suppose you have a class shape with a method calculateArea. If you initially support only squares and later want to add support for circles, directly modifying the shape class to handle new shapes would violate OCP. Instead, you should create subclasses like square and circle, each implementing their own calculateArea method. This way, you extend the system without changing the existing code. Real-life use case: in an e-commerce application, consider a payment system that initially supports credit cards. If you want to add support for digital wallets, you should avoid modifying the existing payment class. Instead, create new classes that extend the payment system, keeping the original codebase intact and minimizing the risk of introducing bugs. Liskov Substitution Principle, LSP. The Liskov Substitution Principle, LSP, states that objects of a superclass should be replaceable with objects of a subclass without affecting the correctness of the program. Essentially, subclasses should extend the functionality of a superclass without changing its expected behavior. Example: if you have a superclass bird with a method fly, and you create a subclass penguin, the penguin class should not inherit the fly method because penguins cannot fly. If a penguin object were to replace a bird object, it would violate LSP because the expected behavior, flying, would not be possible. Real-life use case: in a vehicle rental system, suppose you have a vehicle class with a method startEngine. If you create a subclass bicycle, it should not inherit the startEngine method because bicycles do not have engines. Instead, the bicycle class should only implement methods relevant to bicycles, ensuring the system behaves correctly when bicycle objects are used. Interface Segregation Principle. The Interface Segregation Principle, ISP, emphasizes that clients should not be forced to depend on interfaces they do not use. Instead of having one large interface with many methods, it's better to have smaller, more specific interfaces. Example: imagine an interface worker with methods startShift, stopShift, cookFood, and cleanTables. A chef class implementing this interface would need to provide implementations for all methods, even though chef may not be responsible for cleaning tables. To adhere to ISP, you should split the interface into smaller ones, such as shift worker, with start shift and stop shift methods, and kitchen worker with cook food method. The chef class would then implement only the relevant interfaces. Real-life use case. In a smart home system, suppose you have an interface smart device with methods turn on, turn off, and play music. A smart light class implementing this interface would need to provide an implementation for play music, even though lights do not play music. To follow ISP, you should create separate interfaces, such as switchable with turn on and turn off methods, and music player with play music method, allowing Smart Light to implement only the relevant interface. Dependency Inversion Principle. The Dependency Inversion Principle, DIP, suggests that high-level modules should not depend on low-level modules, but rather both should depend on abstractions. This principle aims to reduce the coupling between different parts of a system, making it more flexible and easier to maintain. Example, consider a class order processor that depends on a database class to save orders. This creates a direct dependency between order processor and database. To adhere to DIP, you should introduce an interface order repository with a method save order, and both order processor and database should depend on this abstraction. This way, order processor does not need to know the details of how orders are saved, and you can easily switch to a different storage mechanism without modifying the order processor. Real-life use case. In a logging system, suppose an application directly depends on a file logger class to log messages to a file. If you later want to log messages to a database instead, you would need to change the entire application. To follow DIP, you should define a logger interface with a method logMessage, and both file logger and database logger should implement this interface. The application would then depend on the logger interface, making it easier to switch between different logging mechanisms without altering the application code. Conclusion: understanding and applying solid principles can significantly improve the design and quality of software. By ensuring that classes are focused, extendable, interchangeable, and loosely coupled, developers can create systems that are robust, scalable, and easier to maintain. These principles not only help in writing better code, but also make collaboration and future enhancements more manageable.